Sound good. So live stream, not that one. Not that one. This one. Okay. So, yeah, those people joining live stream, welcome. Sorry for delay. Had some problem of getting to the RTU location in Liepāja, but yep. So we'll start shortly. So, okay. Right, I don't see it on the screen. Okay, full screen. Okay, cool. Now it is. Okay, cool. So today we will start looking at very interesting details of making these deep learning models. Primarily because this will be the first lecture where we actually start working with the main tool that is being used by all of the AI researchers all around the world right now, which is the PyTorch. Like initially, historically, if you look at the graphs of, let's say, the repositories using all sorts of libraries, initially it was that Google and TensorFlow and Keras was something that people used. Nowadays, nobody uses it. So nowadays, basically, this and even before there was Tiano, there was the before, like, let's say, even MATLAB, of R languages, all sorts of those things, and nowadays everything is just converged to Python, NumPy, Pandas, PyTorch. Basically, those are the main tools for data scientists all around the world. So, and you will see shortly also why this is so. There are many reasons, and it makes life much easier. And you focus only on mathematics, not on the programming aspects, which is the main reason why this happens. Okay, so and we'll look at some of the aspects, and also the cool thing is today we'll start working with proper large data sets. Like, it will not be, of course, as large as in production solutions, but still significant. So we'll look at the used car data sets, and like not just small sets, but we'll look how we can predict all sorts of things there. So this will be the also classification part. This will be really interesting. So let's see. Just a second. We'll get the data sets on. So core stack business deep learning. Where are you? Deep learning, right? PyTorch, right? We have it here. Just a second. I think the best way would be is to just first share the template. So I will share the template, and then we'll look in little bit in the code, and then we'll back to the higher concepts. So just a second. So please get to the Moodle. So I have this right. What is this? Not enough frames. Okay. Hopefully this university's internet will hold. If the live joining people live say that the live stream is chopping up, please let me know. Then I will need to use my hotspot, right? Moodle. Yep. So what I'm talking about here is, please go into the Moodle and get the Moodle YellowRobot. This is my Moodle. By the way, here is also that business course popping up. So if you want to switch to other course, join there as well. So and then also let me know if you switched. Then I will transfer the marks there. So, but basically, you go here inside the deep learning course, and here you will have a template just shortly. We'll add it here. Yep, just a second. So we'll start by the regression task, which is regression means, as I previously told, is the like ability to predict the scalar values, like the prices, the odometer values, the number of owners, and so on. Just a second. Trying to copy things. Okay, cool. So this will be, and classification tasks is to trying to classify if this is a manual, automatic car, and so on. So assignment 6.2, regression task. Regression task. Here is the task. Okay, let's get the template. So it's published, and I will open the template myself as well. Okay, where is the PyCharm loading? PyCharm loading. For some reason my computer is extremely slow right now. Always. Okay. Right. By the way, the template is just one file. It means that if you're working on the Google Colab, then you can run it there as well. So Google Colab means basically if you open up here, so there you can make this Python notebook, new notebook, and you can just copy the code here, and then you could work. Yep, here, but that's one. So I probably need to look why my computer is extremely slow right now. File, open, open, documents. This is weird. Kernel task. Deep learning. Oh, not document vault. Documents. Course AI. Course AI. Right. Yeah, please get the template ready. I'm just opening myself. Course design. Course AI. I have it here. Here. So where is my template? I'll just download the same template as you. Top chicks zip. No. Nokopējās. Okay, ir. Oh, this is not right. Downloads. Save. Saving. So quite interesting. Keep. Okay. Okay, got it. Live. Okay, cool. Opening PyTorch. Open running PyTorch. PyCharm. Let's cancel this one. Share screen, PyCharm. No capture, more than that. PyCharm. Okay, cool. Okay, here it is. Finally, took a little bit of time. So okay, good. So I'll be able to also help if something doesn't work. So so if I switch to a proper environment which is configured, then I don't have anything red here, because then all of the libraries that are installed are installed. If you have any of these libraries red, then what you do is you open the terminal panel and you install the missing libraries. So except super slow computer for some reason, pip install or conda install, let's say torch or some other missing library. So if you install it that way, then you should not have any more red libraries there. So what we want to do here is we want to start by looking at what kind of code we have here, the data set, and so on. So all of you got the file, right? Yeah. File is there. Let's go step by step. So the first of all, there is the class dataset. Similar way as we did object-oriented NumPy version last time, the dataset loads this car deco India dataset where there's like used cars from India, I think like 8,000 of them. And then we have the extraction of this dataset. By the way, PKL, it means PKL, it means pickled data. It is like a binary format. And then we extract it here and I remember this kind of syntax with commas. It just means that I'm extracting tuple. So X is what we want as an input. Y is the output values, and labels are some of these categories. And we will look at them in a second. So if I add here a breakpoint, I will show you what is inside that dataset step by step. We also can see in the comments that there will be some kind of input values and output values, like the brand, the fuel type, the transmission type, the seller type, and as an output value, we will have the oh no, that's not an output, that's also input. As the year made the car, kilometers driven, the odometer, and as output we will have the owner. So where is it? Yeah, the owner type. Is this a private owner or the commercial reseller, and the selling price. And already we can look at something interesting here. For deep learning models, it is always the situation that you can have any data points as inputs, any data points as outputs. So the idea is that it's easy to understand, because if you write in the Flux image generative model, the text, you get out the image, right? But you can also have an image as an input and then categorize, is this a cat or dog, right? So any data inputs, any data outputs. It is from the perspective of deep learning AI models, this is just data matrices, basically this vectors of data or matrices of data. And here I would just want to show you that we can together, like at the same time, predict the owner type, or not, sorry, that's not the owner type, that is how many owners of the car has been. Like, you know, used cars, one single owner, two owners, three owners, right? And also the selling price. At the same time, two scalar values predicted from the inputs. That's one thing to see. So then you will get familiar with this piece of code. There is actually not that much there. You just need to be carefully looking at it. So first of all, the class, which represents the dataset, we can use these operators. So in any programming language, starting from C++, the Java, whatever, we always have operators available for overriding. So here, again, those of you who are not super familiar with Python, we already worked a couple of sessions with that, but this syntax just means dataset full equals new dataset, yeah? So, and then afterwards, if I have this instance of dataset, I can use these operators. So len and get item. So what they are. So first of all, if I use len of this, so this will call this function, okay? So how many datasets, how many data points I have? 8,000 cars, okay? So then the get item. Get item would be just like this. So please give me the first car, okay? It's clear so far? Please give me the second car like this, yeah? And you can even do with Python these things, like give me first 16 cars, right? Like this. So, and it will just call this function multiple times, okay? And give me the list outside. So then next part is torch already gives us nice function to split our dataset in two parts. We have the training part, testing part. So we don't want to have, as I talked last time, the overfitting where the model learns every sample, just the specific configuration of sample, not the underlying logic behind it, okay? So this, remember there were the loss lines, loss plots. So the loss goes down, the error rate goes down, right? And then if I don't have the test set, I can never check if they have learned everything, like the model has learned every single sample by heart. So this is that thing. And also there is the very important this part. We always lock the seed, so we never want to have a situation if I run experiment once, I have one accuracy. If I run an experiment again, I have another accuracy on the same, because we'll have different test sets. Test set is always locked. In a professional manner, you would always have actually 3 data sets. You will have the training dataset, test set, and validation dataset. Validation dataset is something that is small that you run after the whole training process at the end. And the validation and test datasets usually are split out physically as files, not done in the code. But here, for the purposes of simplification, let's do that. Then the dataset loaders, they will also be very simple. Last time we did this manually. So what it actually does, and this is crucial, we already talked about it, is that if I feed 8,000 samples inside my model, nowadays, like if I'm talking about just the car properties, this is easy. Like, you know, I can feed 8,000 rows Excel in the model, everything works. Now if I want to feed like high resolution images of 8,000 like human beings, it will like be not possible, that it will not have enough memory. So then like for example, to predict like identities or emotions or whatever, or even car number plates, whatever, right? So, and that's why we use here the batch size 16, and the purpose for data loader is to split dataset into these small chunks, which is called mini batches, latviešu valodā partīcijas, and this is then processed for the training, right? So we cannot put the whole dataset in, we split it in the small batches. We also don't want to do this one by one. If I do it one by one, the model learns to recognize something in that direction, and the next step recognizes back, so it doesn't move anything anywhere. Actually, also for the whole dataset, if we push the whole dataset in, the gradient vectors are always very short, and they don't learn anything as well. Like remember, we calculated gradients already, so they are important for moving the weights forward. And if I have conflicting information, it will just stay there. So it's kind of this whole topic of optimization based on gradients and mini batches. It's really interesting because there is no really great explanation why this works, but basically mini batches works way better than each sample or all samples together. So that's that. And then the model. This is the model where we have the functions, layers. Remember that AI, deep learning models, which all of the AI nowadays is based, they are just strings of functions, mathematical functions. So there we have this part. Then we have the optimizer. Then we have the loss functions. Some of these very similar structure like last time. And then we have the training loop, epoch. So epoch, again, reminder, epoch means I'm looking with my model to the whole data set. Like if I went through from first sample to the last sample of the training data set, this is called epoch. Then the next epoch, again. So it iteratively goes every time like through the whole data set. And what we want to get is that loss function, the error rate goes down and the accuracy goes up, or some other metric goes up. So, and then very important here, we check if we are in the test or training phase. In the training phase, we apply the stochastic gradient descent, the derivative times the alpha step learning rate, and do the weight updates. Weight updates, basically just weight updates, right? Training step. Test step is running the same model without weight updates, just to double check that it's not overfitted, okay? So these are two. And the structure, how it's coded here, it's also way that you can learn about and this is the common way how in many programming situations you would work. So these are two objects, basically, and here's the pointer, and I'm checking if that object pointer is that, then I'm that stage. So, and I don't need to, there is no like variable is training, is test or something. I could just use the same object pointer to double check if I'm in that stage. So and like it allows me not to make like two loops or some whatever, right? So then here we go to each batches. So this is actually means give each batch, and here we will process the training. At the end, we also have a little bit of plotting, right? We just add all of the losses and plot nicely on the picture. So that's that. So let's then start jumping in a little bit into the first section. If you are running this not on the how would you say, the Google Colab, actually you could do that also on Google Colab, but I don't want right now to divert attention. But if you're running from your own computer, you can just add here a breakpoint and try to debug with this bug button. So I want to show you what is inside the dataset. So if I'm trying to debug it, hopefully it will work. Yes, it stopped here. And if I'm looking at the console, and this is very powerful, like other programming languages, which are not the interpretable programming languages like the compiled ones, would not allow you to do these cool things where you can open just the console here, and they can literally actually start programming here. I can just define some new variables, right? One here, right? Oh, sorry, like this, and then I can just add dummy plus 3, right? And I can literally code here, and it will insert code in that part of the Python. So I don't need to run every time again new like run, right, just to test my code. And this is very cool when I'm talking about mathematics. If I'm just imagine put a breakpoint inside my algebra mathematical graph, and then I checking, oh, this equation is not really correct, or maybe the size is not correct. Super convenient. This, and also of course in any programming situation, Python, and maybe also that applies to the TypeScript, JavaScript, so whatever. These languages which are not compiled, they have some disadvantages. They are slower and so on. But at the same time, you could use this great opportunity that you can put a breakpoint and actually code inside the middle of your code. You don't need to run it again. So why I'm telling about this, because I'm going to show you what we have here inside. So here the labels, right? So if you look at the labels, so self labels. So let's see. So we should have 4 labels, and these labels, what I mean by labels, you will see in a second. So label 0, so you should recognize Toyota, Skoda, Ford, BMW, right? So these labels 0 means the labels for brand, right? So we translate from indexes to human understandable terms, right? So this is just so you to understand the data set. So next let's see what is label 1. Diesel, petrol, LPG, right? So this is the fuel. This is the second part. Again, this will be the index and translated in the human form, right? So then let's move to the next one. So this is the manual, automatic. And the last one is individual, dealer, trust my dealer, right? So that's one. Then let's look at the X itself. So X, let's see how many samples we have in X. So 8,000 cars, and if you would like to look at what is the first car, how looks the first car? So it looks like this. You could start imagining what you have here. So there is the how many kilometers driven, right? The year made, and if you look at here on the axis, see these are the 2 last parameters, 2 last input features, okay? And then there's 4 first ones. Right, and these are indexes, right? So, and we can just try to decode them as well. Just right now exploring what we have as a data set. For deep learning, for data science, the big step, like it's actually, if you're realistically talking, at least like, it would say 50 to 80% of the work, it is based on this end, where you go into in your data set, make sure your dataset don't contain strange anomalies, outliers, so on. Like you clean up your dataset heavily and then you push it to the model. By the way, nowadays, there is another opportunity as well. As I talked in the very first lecture, the deep learning models, which are based, for example, on deep metric learning, generative models, they can work other way around. They can try to help you to structurize unstructured data. But that quality will never be as high as basically clean data set, basically. So the best way how to combine nowadays people do is they use these large models that help them to structure data, and then they apply a little bit of human expert, and then they have like huge advantage. Like previously you had to do like the dataset, new dataset costs, let's say, 50,000 euros. Now the new dataset costs 5,000 euros because you can do this generatively with deep metric learning and then add a little bit of human expert for a few hours, basically. So that's great news. So okay, let's look what is the car x0. So car x0, remember that these are the NumPy arrays. So it means that I can select the, so I selected the first row. This will be the second row, for example. This is the next car. But for first row, I can select also columns. And if I select column like this, like with a comma, right, like this, so then whoa, it should, right, maybe that's not a NumPy array, but then we can select it like this. So this works. Funny thing, but basically, for NumPy arrays, you definitely can select like this. Yep, the funny things that this is a list, but still, like that. So we selected first row, first column, okay? So now we need to translate it. So self labels, 0, and translate what kind of car is it. So this will be the first car. First car is Chevrolet. The second car, so we will have the second row, first column is Maruti. I've never seen Maruti. Anyone from India knows what Maruti is? Anyway, so this is some kind of car from East. So then also the 2, again Maruti. So, but Chevrolet we know, right? So there are some cars that we know. So that's that. What we also can discover. So let's say the label 1. So let's see what kind of fuel it is. So first car, second column, like this, diesel. Okay, Chevrolet's diesel. Okay, cool. Then we can go deeper, the 2, so no, yeah, 2 label, the 2 this, and this is the manual car, and the seller type finally is something, yeah, individual. So this is, then the first car means Chevrolet, diesel, manual, individual. And so again, this is important, we will talk about this visually just in a second. Please try to understand that each of these categorical values are represented as indexes, right? That is clear, right? If somebody not clear about categorical values with the indexes, tell me. So like Chevrolet means 9, right? The other car means, right? Okay, cool. So as for the neural networks, so to say, the what we built last times, right? It doesn't matter. We just can push in these numbers, right, and try to get the output. But there are problems with that. I'm going to show you just a second about that. So we will not do this. We will not push just the raw numbers inside the model. In those cases, when we are talking about categorical values, if we are talking about just the kilometers driven, right, like 50,000 kilometers of 2013, then this is linear or like a relationship. Like if the car is built in, let's say, 1995, they have a similar like similarities, right, between the and the cars which are 2020 have another similarities. Maybe 2020 have lots of computers in them. 1995 not as much. Then with the indexes themselves, they also have, of course, similarities, but this is the index is something that you give. The year of build, this is not what you decide, right? You can just take the Chevrolet will have index 1, index 9, index 10, right? So there is a trick there, and we need to understand that. So let's go to that. And this is important, and not only in deep learning, but in any kind of data science, actually. And we'll quickly move to really hot topic as well. So here, nowadays, everybody is talking about embeddings, vectors, and vector databases, right? Have any of you heard about that, right? No? So this is actually like the way how like, I don't know, like if I look at trends, the vector databases, this is like super hot trend for any kind of computer scientist right now, because you can encode almost any kind of data in this vector format, and then forget about many ways how we process data like in last 30 years in databases. So if you definitely highly recommend, even if you don't want to work deeply on deep learning, to explore the vector databases, because that's the thing that's not going anywhere. That will be like replacement for many things that we did with the relational database. So yeah. So here, let's see. So let me give you examples, and then we will start coding this same thing, and it will make much more sense. But also here it will make hopefully a lot of sense. So here, let's see. Let's take some real examples. So the cars. Okay, so this will be the labels. Yep, label cars. I will look in the YouTube questions as well if you have some now. So there will be, let's say, some of the cars: BMW, then Audi. Then I will use cars which I know. Toyota, and what else? Subaru, whatever. So some of them are Japanese, some of them are German, right? Okay, cool. Let's do that. So then I have these descriptions. These will be, let's say, 3 different cars. So the first sample will be, let's say, BMW. The next one will be Audi, let's say, and the last one will be Subaru, let's say 3, right? Cool. It's nothing wrong about this kind of representation. It's very memory efficient. If I save these numbers as integers, unsigned integers, it takes very little memory in my storage, right? That's great. But for the purposes of the data science, very bad. So why it's very bad? So if we talk about the distances, the similarities, like how similar, what is the distance in numerical sense between these values? So if I look at the distance between, let's say, the BMW and Subaru, so it is 3, right? Between the Audi and BMW, the distance is 1, right? So let's write these things. So here's the white text. I press text here, 3. Okay, cool. So the distance here is 3. Color. Okay, cool. And the distance here is 1. So what it actually means, it would say that if you look at maybe last 2 examples, then the Subaru is three times better than Audi or something like that. Basically, in the same way as the cars built in 2020 are like later stage cars than the cars built in 1995, right? The same similar idea here applies. So that it would just say that one car is better than another car by some scalar value. Because we are talking about mathematics, right? We're talking about indexes, about coefficients, and so on, right? So it doesn't make sense, right? Because what I can do, I can just change around BMW and Toyota places, and now BMW is better than the Audi, right? And this is like my, of course, model will try to fit it, right? And so, but this is your primer, right? This is what you insert in the knowledge of the data, that some kind of there is a relationship, but there should not be. So do you have any ideas how to do this better? Like, do you have ideas how to represent the cars here as an inputs to the model rather than indexes, but something else, or no ideas? Anyone have any idea how we could push inside the numerical representation of cars into model so that we don't have this problem that some car is 3 times better than other car? Any ideas? No?
I would just say add an extra value that shows the class of the maker, but that's...
Yeah, but this is already the value that shows the class, right? The index is the scalar value about the class, but how do you think? Well, another value, what do you mean?
Like that would show what class, Audi is like in the pool wise better than the Opel, for example.
Yeah, great that you're thinking about it. Like the just adding some additional indexes, additional information might help. But there is even simpler ways. Let me show you the even simpler ways. So if we talk about the distances between the numbers, right? So if we just take the same stuff here and do something as trivial as this. So let's see. So what if we just use the vector representations, because we already know vectors, right? Like like for example, if we have where we had vectors, so like the point for the robot arms tip, this is the two-dimensional vector. We had these vectors in the game. Like there's always like vectors is just a list of numbers, right? So here the list of numbers. Let's do this so that BMW, if we know we have 4 car types, we will just use that each car has its own number, right? Number position, and we will flip it as on or off, okay? So there will be 4 slots. That one slot is for BMW, another one for Audi, another one for Toyota, Subaru, right? And we will flip that this is the BMW. Then if we have this one, we will flip this bit, right? If we have this, then we will flip this bit. Is it clear how I represent this, right? So I'm just making from indexes to vector format, where we could just imagine we have 4 columns, and each column will have 0 or 1. And if I'm talking about this car specific, if I'm saying that this is my category, I will flip that bit to the 1, okay? Now what we have something cool. So basically now we have, if you look at the same idea of distances, so you can see already in your mind that if I measure the Euclidean distance between these two guys, within these two guys, what do you see? The Euclidean distances will be different or same? Like what is the distance between those two vectors? What do you think? Like if you, so basically I can also show this on the plot, because now we have 4-dimensional stuff here, but if you imagine that we only have 2 categories, right? Then we will have 2-dimensional stuff, and in 2-dimensional we would have, let's say, so if I have some cars here, then let's say some cars will be, so one car will be, if we only have 0 and 1, so it means that it will be placed here, 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 right? 0 and 1s. And then I'm always looking between distance between these two guys, and so on. So it will always be the, okay, it's not actually, so 1, okay, now it's not actually that correct. It will be just here, here, right? So the distance between, also maybe we can add it here, 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 always between these two guys will be the same, right? Distance. So, and it is the true. So if I calculate the Euclidean distance between just the Pythagoras theorem, right here, we will always have the same distance. Here will be 2, and the other ones also will be 2. So what we achieved with this small trick, which is actually not doing any kind of like intellectual work here, it's just that we made that mathematically now every category is the same, right? It just changes the position in the vector, but it doesn't tell me that this car is 3 times better than other car, okay? So that is already one very cool thing. This is called one-hot encoding. This is called one-hot encoding, OHE, one-hot encoding. And also, this is a probability distribution. We will today also look at classification tasks where we, for example, would classify, is this a dog or cat? And this is also then, that here would be like 100% BMW, 100% Audi, 100% Subaru, right? So, of course, when we will predict things, it will never be 100%. It will say 99% that, 10%, 1% that, and so on. But you already start thinking about how we will represent the predictions. So we will definitely not represent predictions as these 1, 1, 3, 1, 0, 1, 3, right? This is not what we will do. So maybe we can even cross out. So almost like never, actually not almost, but never you would do something like this in any kind of data task. Only why we still use this kind of representations is because it's memory efficient, right? So I can just always save my categories in any kind of data task, not only deep learning, with indexes, but then when I use them, I convert them in different format, okay? But we're not yet finished. So this representation still takes us four bits of four integers here, right? So and there's lots of zeros here, not very optimal. So and also there is this prior. I'm inserted in my problem definition information as an expert from myself that all cars are same way. So I'm saying that German cars and Japanese cars have the same distribution. That I inserted here. I can do better. So what I can do better, and what everybody nowadays are doing even in much higher level, when we will start building ourselves the language models, in this course the plan is till let's say the Christmas, like Christmas, so on. We'll see. I think we will get there. At least we will try to build one large language model ourselves. Basically, the GPT stuff, which is running this, these chat GPT models, whatever. These models actually are very simple. They're really dumb mathematically. The thing which makes them powerful is that you can stack the same mathematics like hundreds of times in layers, or even thousands of layers, make them very large, have a huge data set, run all out, right? And you will get these amazing results. But any student can build GPT models. So, and we will look at, and GPT models and all of these language models are very heavily reliant on the embeddings and vector space. So here, what we can do better, let me show you. So what we can do better is following. To illustrate this even better, let me show you one extra thing. So imagine if we have here X4 car, and X4 car will be also BMW, okay? Is this part clear, right? We have a new car here, right? So, and then, let me show you this. I can also learn my representations. And these are called embeddings. So what I mean learn by them, it will look something like this. So let me, I don't like that this thing is flipping on me. So, okay, so here, I will make it larger as well. So let's see, so we will have embedding 1 here, embedding 2 here. So, and these embedding numbers, they will just be learnable floating point numbers. They initially will be random or 0. And then we will calculate derivative and push them in the direction so that they change. So the idea is that I will feed different types of learnable vectors based on the category which I choose. So this is kind of interesting stuff. I could just build a matrix of learnable vectors, and then if I have BMW, I will choose this row. If I have Audi, I will choose this row, and I will feed it in the model, and I will ask, please change my inputs as well. I will calculate gradient to my input. This is something that I told you before already, that the gradients, remember we calculate gradient to backward propagation. It can go also to the inputs. It can change the inputs as well. So, and this is what we do here. And the cool thing is about this is it's also used for style conversion. You have seen these cool apps where you put your face and it applies, for example, some Van Gogh style. How it's one way how to do this is you put your face as an input, you put Van Gogh on the other side, and you calculate gradients to the model, and you calculate gradient also to your input, and then you change your input, and then it flows the style to your input. That is super cool stuff. And this is the same thing happening here. You just put your random vectors, you choose them by the class, and you say, please flow gradient and change my input. And you will see just in a second. So let's say there will be another E. So this will be E. For the purposes of making it simpler, we could just call it. So this will be the row 1, row. So this will be the row 2, like C, like this. And you will understand this in a second. This is really not that complicated. It just looks in the first part. So E4 1, E4 2, and by the way, the C might be confusing for you. You might think this is exponent, but this is not exponent. So let's change it to Z. So Z, Z, Z. And here I just added this additional card so that you see this point C. This will be again the same embeddings here. See? Z1, Z2. Because that is the BMW, okay? And what now happens, this will be really cool. So now if I'm using this thing, initially when I start training my model, so when I start training my model, then I will have all of my cars, maybe let's say initialized around 0 here or random, okay? Everything is here. Then I train my model, and what happens is that these guys start to move around in this two-dimensional space, because I have two dimensions, see, the Z1 and Z2. And this is also very cool that I actually have 4 types of car, but I only have 2 dimensions. So what happens now is that German cars will move somewhere like this, and the Japanese cars will move somewhere like this. And even if you have this kind of, like just the embedding layer, this is already super powerful. Like you have, for example, if you would flip it around, that these embeddings are not just the inputs, but the outputs, then you could have a model that reads, let's say, and this is actually what's happening in reality, and we will look at these kind of models. I can take a picture of my face. I could learn the embedding model, which would project my face somewhere in the space. And if I take another picture of myself from different angle, it will put it right there. If I take a picture of another person, it will put it further away. So, and the same happens with the language. So it is super, super cool right nowadays that you can have, these are the sentence embedding models, like text to vector, word to vector, and you can have any kind of text represented in that format. If you can understand what it means, this is like revolutionary, because any kind of data nowadays can be represented like that. It extracts out all of the semantic meaning from any kind of data, text, image, audio, data, anything. And then you can build really cool applications on top of that. And if you are able also to build these models which can do this, create these embeddings, then you are like even have more advantage. So, and building these embedding models are actually not that hard. So this is the final representation which we want to look at. I will also show you another small picture how it actually looks a little bit yes.
What are those Z values?
Yeah, okay, the next picture will help to clarify it. The one thing which you look here, notice that Z values are repeating. See, here is and here, see? So again, let me explain. So this is BMW, see? And this is different car. That's why there's different Z values, okay? And this is different car again. And the same way as here is 0, 1. So here's these two are the same as well, see? So, and now let's look at the next one. Maybe that will clarify. So if I just put these representation like that, so here, this is the embedding dimension and your cars or some kind of classes. So on the y-axis here we have classes, not words, but let's say cars or any kind of categories. Here we have embeddings, and we select by index specific row here, and this initially is random, and then we train it to change along the model, okay? So, and also look here how it looks like, another example. So here's another maybe better example. So you could actually you could just select that row by the index, which programmatically is correct way how to do it, right? It's easy, just select index, right? Or you can just use that one hot encoded, do the dot product or with this guy, and you would select that row. And this is, so basically every time when I take BMW, I will just take the first row. Every time when I take Audi, I will just take the second row, okay? And initially all of this is random, and when I train the model, it starts to float around in the right spaces, okay? And then I can use the embeddings themselves, I can use as a piece of information, very valuable piece of information. And this is the vector databases. This is all of the, like, this is the super important thing for any computer scientist to understand. Nowadays, you would not be able to live without vector databases for long. So, basically, as again, I say, databases, old days you had like select by like or something like that, right? Like similarity or BM25, whatever. Nowadays, everything is moving heavily towards the vector representations. So you need to kind of understand this aspect. So that's that. So now let's try to code all of this inside our template. And then the first task will be just for this price prediction, and the number of owners prediction, but then we will also today try to also do the classification part. Yeah. So, but the classification is not that different from what we just talked about. So this is this. So here, what we see, some of the interesting parts. So the x. So the x here, all of these things. These are actually standardized. You see the mean value divided by standardization, and the important part is to notice line 39 where I cut only these two last things. So in the x here, actually what we have at the end is it is just the year made and kilometers driven, and these are now standardized in the format from -3 to 3 or 3 sigmas format. So basically this part is just standardized. Why I'm standardizing it, again, remember that years are let's say 2020 and kilometers driven let's say sometimes 500,000. We don't want to feed such a huge difference in data, right? We're trying to normalize everything around 0. But then we also have these guys. These are the classes, right? And let's see. So in classes, we want to push them, yeah, here. So classes are split out here, the first indexes. We don't touch them. We don't normalize them. We don't do anything with them, okay? Cool. So that's that. Let's move down. We don't have implemented yet the data loader, data loaders. These are very simple to implement. Let me show you that part because those are already built. Today we will look at many things which are already built in PyTorch, which will make our lives very easy. So we'll just like playing with Lego basically. Torch utils. There should be data something. Yeah, data loader. Data loaders, and data loaders task is to change from just any number of data points into these mini batches. And I'm giving the dataset. The dataset must be in the Torch utils dataset format. So I'm just giving the train dataset here. Then I'm giving the batch size. This is called hyperparameter. This is not learnable parameter, but parameter which I give as an expert. And normally, when I train any model, any deep learning model, this is one huge mistake that with what I commonly see, that programmers take, let's say, from GitHub YOLO, train the model, and think this is done. They probably get one of the worst results they could get, because actually what you need to do is to search all of the hyperparameters. So you would not feed only, let's say, 32 batch samples. Maybe you need to also test 64, 16, all of these combinations. There's a huge combination. This is called grid search. So if you don't do that, you just press train, you will have suboptimal bad result, basically. Even if the result is acceptable, you could have much better result. So that's that. So batch size, then shuffle. This is also cool. This means that please, every time when I enter this loop of data loader, give me the batches in different order. So it is, because as you can imagine, if I train my model, if I'm starting to go in some valley, and if I do this always the same way, I will very quickly go to some point which is not optimal. But if I change it around, it might go over some valley. So then another one. Drop last. Do we need drop last? Let me think. Okay, let's do drop last. Drop last is actually necessary that if I'm calculating some kind of normalization, I don't want to end up in situation that my last batch size is size of 1. Then it's very, like if I split it by 16, 16, 16, and accidentally my last batch is 1. This is kind of very bad situation, because then it will, train some things in not so great way. So how to do this is also very simple. Data set train, and then do the modulus, right? This is division, what we left out of the division. And if the division gives us 1, then I want to drop last. Let me check in the YouTube. Hopefully that works. Okay. Yes, thank you for likes in YouTube's. So just make sure that that it works. So okay, so it seems to be, because my internet here is not great. I was thinking that university's internet is a little bit better, but okay. So data set like that. Then data set of this. Data set on this will be the second one, will be test data set. That data set test like that, and batch size the same. For test, actually, we don't care about batch size. We could just run it in one batch, but again, just for the use that nobody actually, like for the tabular data, we could just run all at once. For any other data, we would not have enough memory in GPU. So, and you will see in next time, we will look how all of this code can be shipped to the GPU just with one line, basically. So this is also super powerful. Why PyTorch is super powerful, that you can, everything that we write here, we can with a couple of lines do on graphical processing unit, and specifically NVIDIA CUDA, because all other guys like AMD and other guys, Intel Habanas, whatever, it doesn't work. So it's this is kind of funny thing that NVIDIA started investing on this like 15, 20 years ago on the mathematical layer, on the libraries and so on. All other guys is so far like behind. It is super hard for them to make their, because you know that recently there was some kind of GPU grok coming out or something like that. They were also claiming that, okay, you can run faster inference, things like that, but the problem is that you try to run your model and then there is some kind of mathematical operation which is not supported. Then you just, what is that? I don't have time for this. Like, let's move back to NVIDIA. So basically, that's the reality right now. So then shuffle you want false actually, because you want that every time when you debug with breakpoint, you have the same sample for the test set between epochs. So you doesn't have like, now I'm looking at this car, next epoch I'm looking at different car. Very strange situation. So that's that. Okay, so I'm putting these two blocks to the whiteboard, and then we move on to the next step. So this is going to the whiteboard. And as soon as we will start run this stuff, I will go around the class and make sure that everybody have this working. So this is pushed on the whiteboard. So then the model goes here. Model, and the model will be really fun. Like at least like if you enjoy anything about AI, so there will be really nice way that you can play like a Lego basically. So here, and this is similar to Keras old days. So torch, NN, sequential, and why we could actually, you don't need to write like this, but you could write like this as well. But if you write like this, then it will not automatically find parameters function. If you remember last time we had the parameters function, which goes to all of my layers functions and find learnable parameters. But if I'm using torch NN sequential, then I can automatically find all of the parameters. So, and then starts the fun part where I'm just using the torch NN linear. And then this is a linear layer, basically x dot product y plus b, or affine transformation. So and then in features, and in features also very simple. So we have two scalar in features. So maybe I will just copy them up here so nobody gets confused. So because this is really simple, but of course if you're just looking at numbers you might get confused. So here, let's say years and kilometers driven. These are two input values, okay? And then we have 4 categorical values, and this is what we just showed on the whiteboard. We say 4 times embedding size. And what we will do, we will calculate these nice vectors, and we will concatenate them in the sausage, and then we push it to the model. Clear? Right? Like we showed you previously on the whiteboard. So, and then next comes the out features. And this is, remember, this cool, super cool feature of dot product of this two-dimensional mathematical algorithm, where I do the, like the matrix dot product, I can project high dimensional data into lower dimensions, like literally those who were like the shadow, right? This is not a great example. If I have something of a shape, so like this, you know, this is a irregular shape, yeah. And if I have a shadow of this, right? So this is the projection. So I have multi-dimensional shape projected on 2 dimensions, and this is the same thing what does the matrix dot products, right? And then we can do even cooler. We can take that shadow and predict what is the multi-dimensional object as well. That we can also do with matrix multiplications. So and this imagine also how much it affects everything that you with data. With data, there is many methods, not only these methods where you can project down data, project up data. There is even, like, if you do your bachelor thesis, master thesis, whatever, you will present your data. You can have lots of columns, and then instead of showing columns, you can just have a nice graph with dots where, like, the similarities are captured, that they're projected down to 2 dimensions, for example. Like, this is really valuable. So that's that. And let's see, so out features. Out features we will have, let's say, 16, but this is something that we choose as we want. And remember I said normally it is like a neural encoder. We start with very high dimensional, low dimensional, low dimensional, low dimensional. So like that. So then torch and relu. So this is the nonlinearity function, which is like everything that is in the minus becomes 0, everything that is 1 over 0 becomes the same value. Like, so that's nonlinearity. I talked about nonlinearity last time, where we have the projections, and if I pull out the data, I can cut them off. So this is really cool stuff. So that's that. Then next layer is we will push it down. So from 16 dimensions to, let's say, 8 dimensions. And we could again add some nonlinearity here, and we'll keep pushing it down till the dimensions what we need. And again, the number of layers, the architecture. The architecture is something that you can invent yourself, or you can take what other people have found is good architecture. But the hyperparameter still changes. So why 2? So the out features are 2 because we are predicting the Y. So we are predicting Y owners, how many owners have been this car, and Y price. So we are predicting 2 things at once at the end. Even if we will predict just price, it will also be in the vector format. It will be just vector 1. It will never be just one scalar number, because we are talking always we're talking about vectors. We're talking that we have a batch feature size. Basically, that's that. Okay, so please make this small piece of code, and then let's move to the embeddings. So self embeddings. So an embeddings will look something like this. So there will be, and this will be also very fundamental, because we will use not sequential but module list. And this is module list is basically the same thing as Python list, but it is a class from Torch, and this means that it will still try to find learnable parameters, because we will want embeddings to be changing, not fixed. So, and why it is fundamental, because basically what we can do, we can build really cool mathematical models. It doesn't need to be like this function 1, function 2, function 3, function 4, it goes down. It can go like this, like functions out, function goes back, goes out, goes back, goes out. We can build really crazy mathematical models. And this is actually what's happening. Even in GPT type of models, they also have multiple paths going on. So this you can do with that. So this will be the multiple path idea. So the embeddings, and we will have 4e in range. And why in range? Because we have 4 different these categories. So we have brand, we have they're actually up there. So we have fuel, we have transmission, and we have seller type. That's why we have 4 there. So, and for each of these, we will produce their own embedding table. This is what I showed you before on the screen. So append, and there will have torch and embedding. Yep. And this is really like glorified weight matrix, basically. I could actually have torch and then parameter weight matrix. This would be the same thing. It is just like cool name and also basically optimized for selecting values. So this will be torch and an embedding dimension. Again, this is super powerful. This means that I can have any embedding dimension. I have a 2-dimensional, 3-dimensional, 256 dimensions, even though I have 4 types of car, for example. So that's one. And then number of embeddings. This is fixed. This means how many types of car I have. So dataset full labels I. So this exactly. So like that. And this is basically all of my model code so far. You'll be able to do great things with this model code. So yeah, I'm now putting this on the whiteboard and letting you to finish up with this. And then we will have the forward pass, then we will have the optimization part, and then we will have running model, basically. Oh, okay, just second, looking, I'm just posting in, which line? 110. You mean this? This?
The comma, yeah.
Comma, ah, right. Yeah, yeah, you're right. I think it might work, but let's remove it, because the funny thing here is that you see I'm giving any number of inputs, so it will represent it as probably as a tuple or list, and then I can have these extra commas. But still, cool. I like that you check on me. Like as always, when I'm doing these things with live audience, it's always great that like it's an intelligent debuggers. So like it's great. So yeah, did you do it? Right? Okay, cool. Let's move on. If any have problems, raise hand. I can come and help. Okay, cool. So then the forward pass. This is also be very simple. So yeah. So let's start by first. So the first part is we need to get those embeddings ready. So x embeddings. So this will be the list of those magical numbers which we will plug out of those matrices. So for e in range of 4, and we'll plug them out. So each, let's say each whatever. So self embeddings e, and how we will do this is by calling forward. And here there will be a tricky part, X classes, and I will explain this. So what I'm doing with this one is I remember that X here, maybe I will put it here. So the X in the forward pass will always comes in the format batch, comma features. And I'm here selecting, please give me the embeddings for every single car that I'm having in the batch. I will have 16 cars. And each of the 16 cars will have different embedding. That's why I'm using this notion here. It basically just means from 0 till n of X classes. I will definitely not write it like that, but for those of you confused, it basically means that this, exactly this, so X len of X classes, okay, it will seem strange, but basically, X classes, no, right, it is X classes, okay, yeah, it's just classes like that, basically. Yep, so it means that. If you would put a breakpoint, you will see that there are 16 cars with each of them separate embeddings. Okay, cool. So what I do next, I will create sausages. So here, cross sausage creation looks like this, because I have 4 different types of embeddings for each of the cars. So I'm adding like that. So these are added. And next I need to, so embeddings are concatenated. No, I need to concatenate them somehow. So embeddings, okay, let's concatenate them. So x concatenated, torch cat. And concatenate means, so I will just show you in a second. This is nothing like really difficult. What it actually means, this line is that, let's say if I have if I have here something like this, like just to give you a comment example, A, B, C, C, D, yeah, and so this is this, and then if I have, let's say, so this is that, and if I have here, let's say, another set of square brackets, so this is the first sample, another sample, E, F, G, H, so, and then this will produce basically the same data, but I'm removing that extra dimension and create sausages like this, for example. So chick. I believe it should be like, I can actually remove that extra dimension as well, but the main point is basically that you will get something like this. You understand this idea, like concatenation, right? I'm just taking the same data and in some dimension, like putting them together in the same list, basically, right? Like if there had two lists here, chick, I'm saying now please make a sausage here, okay? So that's what does this line. So it changes, again, we have these 4 types of embeddings, and we're putting all of them together in large sausage for each of the cars, okay? So that's that. And then finally we need to put all of this together in so let's add also the existing data. One line before this, append X. So this will also append in my sausage the what was the kilometers? No, not kilo. Yeah, I forgot what we had in the input. Year and kilometers driven. Year, kilometers driven. And then now the final sausage is basically this. So all of these guys plus kilometers driven, and all of this now is a numerical format. There is no indexes. There is no nothing like that is pushing model in the wrong directions. Everything is very nice and clear. So this is then the final input for the model. And then the model output is also very simple, like the same structure as we tried to do last time. So the self layers, forward, and xcat as an input, like that. That's about it. You don't need comments. Without comments, it's very short. So then the big difference from last time when we worked with NumPy is that we don't need to write backward pass. If we want, we can, please don't write it, but we can write backward pass here, which means that I want to calculate the grad. Remember grad? So for each of these guys, we still have in PyTorch this thing, dot data and dot grad. We don't need to write this, but basically we always have these two things for any tensor variable everywhere in the PyTorch, okay? And this is exactly the same thing what we did with NumPy models. We calculated the grad ourselves. We pushed the data ourselves. These two values are always present. It's just we don't need to calculate them, because if you want to try this out, if you just take any kind of derivative equation, put it in Wolfram Alpha, or nowadays also in GPT models, it will give you the response, right? So, how they do that, at least in the Wolfram Alpha, is that they take the derivative tables, do the chain rule, and apply to each of these, and do this automatically. And this is called autograd. And here in the PyTorch, we have autograd. So that's why the kind of like the happy thing is that this backward pass is not needed. But at the same time, you need to keep in mind that for really complicated models where you cannot derivate functions, you can implement your self-gradient in PyTorch. Like for example, in reinforcement learning models, couple of them, you could, or there's also really cool other types of models, like for example, the variational quantized autoencoders and so on, where you can make your own gradient without mathematical autograd. So, but we can delete this. So we can delete this, and that's a good thing. We don't need to. We can forget about gradients for a moment, which is I think really like a blessing for students, because then you don't need to calculate gradients, but still you need to understand a lot of things. So I'm just copying this part as well. Now let's move on to the next one. So we have optimizer. Again, optimizer super simple to implement compared to what we did before. And what optimizer does is I'll just write in a comment. It's again very simple thing. So optim, we can use some SGD. So this is stochastic gradient descent, or we can use also all sorts of fancy optimizers. So the best fancy optimizer is Radam. So you can just use Radam. Radam is the least susceptible to learning rate. So model, parameters, but they all do the same thing. So I will show you what they do. So learning rate, like that. So these 3 lines. And what they do is what we already discussed. So it is changing the weight. So it's taking the weight equals the, so weight, so the loss, the weight times, so okay, let's say, so this will be the minus, so weight minus, so this will be, let's say, prim weight till alpha, and alpha is the learning rate. Remember that equation, stochastic gradient descent. If I have the gradient, it gives me direction where I need to go, and I change the weight. And this is what basically the optimizer does. And these fancy optimizers also remember the previous time when I called the optimizer, and also calculates the momentum, so how fast I go. So this is useful. That's cool. So I'm adding this to the whiteboard. Now we have the loss function, the last piece of equation here. Loss function. In PyTorch, there is also built-in loss functions. Highly not recommend to use them, because you will see in the classification tasks that it might go really wrong. So loss functions. So let's see. So the simplest one, mean square error, torch mean, torch mean, and y prim minus y and squared. So this is how you write in Python squared, like that. And that is about it for the loss function. Very simple. And you can invent your own loss functions, which is really cool. Actually, the many loss functions that are very popular nowadays are not statistically derived. So people, like, this is like a great opportunity for all sorts of research, because like it's not like that everything is discovered yet. So you can do these things as well. So that's that. So this is loss mean square error. So if you go down a little bit, so there is the actual learning loop, which also will be just a few lines, quite simple. So here y prim. Y prim means this, or it's called y hat, whatever. This is the predicted value. So forward x classes. We can define as many inputs as I want, like that, right? X classes. We can pre-process it, whatever. Loss function forward. Y. Okay, and then we need y prim and y, like that. And finally. Yeah, so loss. Yeah, I want also to have the graph, right? To just plot what we have. So loss append, and we'll have loss, and the item function means the same as loss data 0. I think something like that, or 0. Basically, that is the same function of loss item. If I have just one single scalar value deep inside some kind of array, I can just call item and it will get me out of this. So that's that. Then for the training pass, if data loader equals data loader train, then we will do extra step, and this extra step means loss backward. We will calculate gradients, then we will change the weights, optimizer step, and then we will clear the optimizer weights, optimizer gradients. Basically, the clearing of gradients is again one part which we talked last time, is that we always plus gradients, plus, because we can artificially make larger batches. Like for example, I cannot push everything in single go. I can add more samples, and only then call step. So I could theoretically call backward multiple times and then only do the execution of step. This is very important for recurrent neural networks. So that's about it. So now I will try to run this whole code. If I have some bugs, we'll debug it. We'll go around, check if it works for you, and then we will need to discuss the classification as well. So run. Run. Let's see. Okay, so the loss is reducing, it seems, at least for me. Okay, the plot is showing. Okay, seems nice. And then maybe if I keep running it, at some point it might start to overfit. It might start to start going up. But I believe actually it will never happen because I have very little weights here. I will go around and check how it's doing for you, but just to show you overfitting, I could try to add something extra here. It will take a lot longer for me to train it, but at least maybe you will see some overfitting. So 5. You don't do this for yourself. I'm just changing it here to show the overfitting. So okay, let it run. Yes, and hopefully it will start overfit. So the overfitting also happens when you have too many parameters in the model, and this is actually standard procedure for building models. Okay, anyone running this? Working?
Yeah.
Okay, this works for you, great. Okay, error, it will help you.
I have.
Okay, cool. So it works.
So in the Discord?
I think I missed something.
No worries. Let me see. So and then embedding has no attribute or to neprežužiti.
Yeah.
Okay, spalīdzēšu izdomāt. Okay, kā tev Okay, super, awesome. We have many people running already yet, so how is it? Oh, you're not coding? Okay. You're not coding? You're not coding? Okay, those of you who are not coding, if you want to join the other course, like you can also, reach out in the email. Okay, cool, I will then. Okay, cool. Then I can put you there, because in this course at the end you will have, see if there is overfitting. That's super cool. So at the end of this course, you'll have the paper exam where you have to do the mathematics on the paper. So basically, if that's not something that you're up to, then maybe you can go to the other course. But those who are able to run this code on right now, it will not be that difficult. So it definitely don't give up. So okay, cool. So we have a couple of people running it.
I had an issue with NumPy.
NumPy libraries. Okay, if anyone else can look, so we have at least half of people running the code, half not running. So this is actually the overfitting, and this is super nice picture. I love it because basically you need to save model now at epoch 20. Basically, if you save model at the end, this model will be bad model. You understand? Because it will be learned every card by itself, not the logic of the card. Because it's the test dataset is starting to give me higher error than the training dataset. This is like typical overfitting situation. Okay, so that's that. So we need to move to the concepts of the classification. And even though if you're not running the code now, it's still valuable for people to understand about classification. So I will just check in also in the live audience. Okay, live audience, right? Okay, cool. I will also later add for anyone watching YouTube later the templates to the description. So let's move to the classification. Classification is also super exciting, super interesting stuff, because classification allows us, to predict if let's say buy or not to buy or things like that. Let's see. So for classification, I have some kind of small nice pictures somewhere. Okay, so for classification we'll do this. We will have multiple outputs. So right now we had two outputs, right? The number of owners and price, right? But for classification, we will have many outputs, and you can imagine what those outputs are. For example, let me see actually what will be the next template. In next template, I have these classes laid out there. So to CC template, I will just find it when my computer will not stop spinning rainbows. 6.3 template by date, template by date. I just want to check what kind of outputs we are predicting. Okay, fuel type. We are predicting fuel type. So let's say we will have fuel type. So Y fuel type, and this will be petrol, diesel, LPG, CNG. By the way, CNG cars. Have you seen any CNG cars? Like I have seen CNG stations. I think it's very hard to get drive CNG car nowadays. So doubles gas, like I'm tired. So these will be the outputs. Okay, let's see. Oh wait. Okay. Yep. So this will be nicer. So, and for these outputs, we will predict four values basically. So the last layer will not output just 2 values, but 4 values, right? So, for example, here, let's say the yellow one will be petrol, right? Then the red one will be diesel. Then this one will be LPG. And the last one will be CNG, and we will not have those other values. So basically, all of these will not be there. Okay, is it clear so far, right? So we will predict the last linear projection, this last shadow, so to say, will give us just 4 outputs. So this okay, well, it's not allowing me to move this thing. Okay, this is not cool. Okay, let's delete them as well. 1, 2, 3, 4. I don't want paint coloring here or whatever. So anyway, so this is that. Just 4 outputs. If I just put 4 outputs of my model, it will just give me any numbers like minus infinity, plus infinity, right? It's not good. Minus infinity, plus infinity, not good. So that's why we apply a function called softmax function till to the last layer basically, and last layer is called logits. So it's here written logits. So and what it happens is this. So if you see, if I add softmax function, immediately from like any kind of numbers from minus infinity plus infinity, I get probability distribution out. Like I get that the highest number maps to 19%, the lowest number, and so on. And basically the softmax itself is an approximation of, let's say, hard max, because basically what we want the model to do, we want model to actually output us not this, but model, if in the perfect world, the model should output us something different. In the perfect world, it should output, right, how can I move this guy around? Okay, let me, right. It should predict one hot encoding, so it should predict 0, comma 1, 0, 0. So if I get this kind of output, I would be actually very happy, because this is basically the same as my training data, right? But in reality, we cannot really force mathematics to give me this number, right? Like there is a thing called argmax, where I can just take argument maximum value, which means that the second index is that one, but this is also not derivable. I cannot make derivative of that, and also the like this hard max is not possible. Also, if I'm applying, let me see if I have a picture. If I am applying just the simple, yeah, I have it. If I'm applying simple norm max, so all of you have done norm max in some way. Like I believe that in any kind of mathematical situations where you program something, you would apply norm max often. So for example, weight normalization. So let's see. So here I have Hardmax. Hardmax is something that I cannot use in mathematically because I have no derivative. Normmax is where I just have summation and make sure that everything sums up to 100%. But then then the softmax, right? And then what we have, normmax, hardmax, perfect. Cannot use mathematically. Normmax gives us like this strange situation where this one value is not as close to 1 as I would like to be. And softmax push it is closer, right? And again, this is not like put in stone. This is super cool. You can also do research, and I have seen some research on improving this, because the softmax doesn't mean to be the only way how to do this. So, but like these small fundamental pieces, it's hard to do research because many people have tried it already. But there is many other pieces which you can do research. So that's that. Then let's look forward. So the next thing is we could actually, if we have the output like this, train we're using the mean square error. But mean square error is not the correct way how to do this. The way how we need to train these models, oh, okay, I accidentally copied this, is to use the information theory. And in information theory, there is the categorical cross entropy. So let me see, I actually have one pre-made template here. Why it's not copying? So copy again. Okay, let's see if I get it here. Okay, cool. So this is just from my notes. But basically, categorical cross entropy looks like this. And I will just in the next slide we'll show you basically it is not complicated at all, and it has some really nice properties, and it actually comes from the information theory where you estimate the bit loss. For example, you have digital translation, digital, how you say, sending data over Wi-Fi or whatever, and you want to calculate how many bits could be lost in different situations. And then you have the entropies, then you have the cross entropies, then you have what else? All sorts of these. Also KL divergence, all sorts of these things, and you can actually build these mathematical theories. And if you apply the same theory here, it kind of works really nice. So and that exact equation actually is this one. This is that equation, and what it actually means. This is not complicated at all. If we write down it, so the y here is the real target value. So let's say this will be the diesel car, right? This is the vector y for each of the cars, right? And then the predicted will be here 0.9, 0.1, and so on. So this is y prim, right? You plug in these vectors there, and you calculate one by one logarithms. By the way, the epsilon is just so that I don't get logarithm from 0, right? So that's just the only thing. And then you get the output value, which will be negative, and this will drive our gradient. And we'll look in just a second how it actually drives the gradient. So here, this is the logarithm function from 2. Actually, from base of 2, it's really nice to see that basically if we do some thought experiments here, let's see. So if you look from base of 2, so if the logarithms, so here on this side, logarithms from base of 2, so for logarithm of 0, it will, so logarithms of 0 will be here 0, and for logarithm of 1, by the way, this should be, so sorry, it's a logarithm of 1, logarithm 0 will be very large negative value, so let's write it here. So this will be then, so logarithm of 0 plus epsilon is like large negative value, so 999 whatever, and the logarithm of 1 here will be 0. Okay, great. And then every time when these two numbers match, we have 0, And any time when these numbers doesn't match, we're starting to get really large negative values. And this is great way how to push please get to the right place. And it is also coming, we could do the same thing with mean square error or other things, but they will be very smooth. These are really pushing very hard to getting the values 100%. And this is also important. Anytime you use some kind of classification models, or segmentation models, even like YOLO or something, it gives you the confidence on class. Any model that is trained with categorical cross entropy will never give you good confidence for multiple classes. So it is like bad idea to use classification model and think that, okay, if it gives me 20, like let's say 50-50, well, it will never give you 50-50, but let's say it will give me 30-70, that this is similar to other class. It is useless information, because the model is always trained to push just on one class. You can build models also for multi-class classification, but they are trained with KL divergence, so this is different way. So, okay, cool. So that's that, and now let's look at that template and show you how in reality this looks like. It will not be difficult to move from this regression task into classification task. So just a second, I'm putting this also on the Jamboard, no, on the Google, on the Classroom. By the way, let's do this another template, and then we'll wrap up for today. But basically, bear with me so that we do this together. Right. Okay, so this will be implement PyTorch version of classification task. There is also really interesting other small subtasks which we don't have time today to go through this. If we go through each of the subtasks, it will take the whole day basically. But there is also confusion matrices, F1 scores. I highly recommend for somebody who really want to be like an AI expert in future, or deep learning like scientist or anything, or like, because we even, just for the perspective, the Google earlier this year fired like I think it was like 2 large departments of programmers, and now they're saying that 25% of their currently produced code is generated by AI. So what it means is, in near future, that we will need a lot less programmers. Basically, not many programmers, but we will need more data scientists. Basically, so that's something to keep in mind. Like to get a good job, probably you need to kind of learn all of this stuff. So basically, this is this part. Okay, so there is a template. Let's take that template. I will also take exactly that template, so I don't accidentally copy something else. Save. My slow computer showing something up. Did this save? Keep. Please open that template. Will help you to get through there. 6.3 template. Live. Copy. So I'm copying it here, and now I'm moving to the Python code. Checks. Python 6.3 live. I will see if I need to copy some parts of code from previous template. So let's see, zoom in. We'll see what's different in this template. So here, yeah, there is one small difference here. So you already see up there we have some kind of tree here, right? So this means that we are cutting out the fuel and moving fuel as the output value. So the fuel is now the output value, and all of these guys are the input values. Okay, so I just shifted around a little bit the values. So that's one big difference here. So this is now the output, and this is the input. And now I'm also writing here in the bottom part that we need to do the one hot encoded outputs. So I previously told you that one hot encoded embeddings, like for the inputs, that's not cool, that's not great. We can do better with the embeddings. But for the classification, if I use the categorical cross entropy, I need one hot encoded outputs, like the 100% precision. So there are ways how to train categorization models that don't use this property, but this will be super complicated. We will look at that later. So this is the outputs. These are the inputs. Okay, cool. These are outputs, inputs. Let's go down. Here all of these things are kind of the same, except I forgot to add here the drop. Then the model itself, I think we will be able to copy the model here. Loss categorical cross entropy, we will implement that thing. We go there, and then the actual execution also is a little bit different. But we will be able to copy small pieces of code and actually make it work the same way as before. So let me now to just get on top of things. I will look at the previous code that we just did, and we'll try to make it work. So okay, so let's use the simplest thing that we can do here. So there is written that we need to actually I have these to do. So yeah, let's do the to do. So the line 70 something here, one hot encoded. How to get to one hot encoded? So what it actually means, we need to have diesel as this representation 0 0 0, yeah, and then the petrol will be this, yeah, 0. We can make a for loop and just produce these vectors. This is not wrong. You can do that. Or I have also built-in PyTorch function that does it. So from this, so what it actually means, let's say there is an index 0, index 1, index 2, index 3, that. And to do this, there is the function called the function called self x the f1 hot encoded self y so f means torch and then functional on hot encoded. So if you look, I don't want to scroll around here, but if you look, then it is something like import torch and then functional as f. This is just like simple way, like the same way as numpy. Remember NP, everybody writes NP. So that's that. So f, and here will be torch, and no, not nn, but long tensor. Long tensor is just the, so it is like an integer value. So, and here we'll have the y's, and it will just immediately produce the format of these vectors. So this is really, really nice. Also, one thing to notice here, which is very important, is that now we have at least 3 major big data types. We have Python lists, right? These are Python arrays. Then we have NumPy arrays, and then we have torch tensors. Torch tensor. So, and you can go in between if you choose them, like to NumPy, NumPy, then tensor, then to the list, to lists. Remember, there are these functions. Like for example, here to go from NumPy to list, there is a function called np. So there is a np array. Let's say array to list, right? Something like that. And why I'm telling you about this is because even though I have list, NumPy, and torch, there is still not a situation where I'm just using always tensor, always list, because each of them have different things which are good about them. For example, lists, super easy to have append. Now if I'm talking about tensor, which might be also on the GPU, then it's not append. It's like reserve me memory, put something inside. It's totally not cool. Also, here is the torch tensor CPU, and there will be also torch tensor CUDA. So we will have even like that. So there will be 4 layers of different data structures. So that's something to keep in mind. So I'm putting this in the whiteboard, and now let's move to the next part in the code. So this will be on the slide number 14. So move down. Right away here on top, we will not do this now. We will not have time for this now, but basically there is also the weight. So this is not trainable weight. This is how many cars I have with diesel, how many cars I have with petrol and LPG and so on. Because what I don't want to have situation that if I have only a few cars with CNG, then the model will never predict CNG because it is easy to predict diesel and petrol and not those. And what I want to do there is to create coefficients to move my loss function so that for the rare cars I have more gradient capability. So that's something that that to keep in mind there exists. So then if I scroll down here to the model, for the model I believe we need to just copy all of that what we had before. I will just do it here. Right, where is my previous code? Interesting. Okay, here is previous one. Wait, okay, it's up here. Okay, cool. Now I see it. So this is literally code we just made. Please go to the previous template and copy this constructor part to the here. We will just make a few small changes. So the few small changes which we will make is the following. So first of all, we will predict 4 output values. These 4 output values will be petrol, diesel, LPG, CNG. So if I would like to predict multiple class distributions, let's say the fuel type, the car transmission type, and so on, I could just keep adding in the sausage and then split them out, do different loss functions, combine them like that. So this is that part. Then the other thing is we will need to remove the petrol stuff from here, up there. See the embedding? There is from 4 to 3. So that is, and we will need to add the owners and price up here. So it is kind of interesting thing that we will predict the like petrol, diesel car from all of the other features. What we could also do is predict brand, for example. That would be even more interesting because the price might correlate, like Mercedes are more expensive or something like that. So, but yeah, here is the inputs. These are 4 scalar values, 3 categorical values, and output is just for 4 categorical values here. And don't worry about these 5 because that's what I just changed myself. So you don't need to change those numbers. Just this part and this part, right? So here 4. And also here, basically we need the 3 embeddings there. So 3 embeddings. I will put this in a second on the whiteboard with color coding, that so you know these 3 small numbers which I changed. So basically I changed 3 small numbers. Oh wait, before I put it on the whiteboard, I just want to add one more thing. So the new thing goes here, torch and n softmax. And dimension -1 means the last dimension. If I put just 1 also would work because the dimensions are batch and features. So always batch is the first dimension. So if I add breakpoint in the middle of my forward pass, I would see that all of the mathematical operations are always executed for each of the cars in the batch. Like it's not that, like we always have 16 cars, for example. So so that's that. I'm adding this to the whiteboard. So these changes done. Yeah. Okay. Cool. So then forward pass. Forward pass again. Let's copy the same code as before, and again let's change like just a few numbers. So here I'm just copying this same thing from the last time. Now we will have not 4 but 3 here because I removed the fuel type from the inputs and moved it to the outputs. So this is that. What else? Do we need to change anything else? I think that's just it. Yeah, I don't think that's just the one number needs to be changed. Anything else needs to be changed. So yep. So this is this. So this is cool. So just one number, very easy. So slide number 16. Then scroll down, and now comes the fun part with the categorical cross entropy. Why it's fun? Because you actually can design your loss functions with simple equations and do really interesting things. So here we will just write the same loss function as for the statistical, like this information theory. So it means here it's minus torch mean. By the way, I think sometimes you write also sum. Sum and mean doesn't make, like you can use sum or mean, it doesn't care. But the problem is that sum means that I will sum all of the 16 cars together in the loss. And what happens if I suddenly decide batch size 32? It will be again sum of that. Everything will work, but the learning rate will change. Learning rate will be affected by the number of samples in my batch. So that's why mean is better, because then it's even less dependent on learning rate. And in the deep learning, there is so many moving pieces, as you see. We want to reduce the number of moving pieces. We don't want to make more non-moving pieces. So that's that. So then y, and here we don't use dot product, but pairwise multiplication, or they always sometimes call it Hammond product. Pairwise means I have two vectors, and each cells are multiplied by them each together. Not like if I do the dot product, I would turn vector like this and make a matrix out there. So like that. So torch y prim plus epsilon. Epsilon is always the smallest floating point, so like 16 bit floating point number. So this is e minus 8. So, and by the way, this is also an interesting, fun topic for any kind of programming. If you ever work with floating point numbers, like numbers with dots, you know, like the decimal numbers, programming is very, so it is very important to know what is your limits for that floating number, because you can have, it can literally give you examples. So you write, let's say, like so 99,999 plus something. And if you add too many numbers by the comma, it will just give you 0 or some kind of strange number. And like I would say, 99% of programmers are not realizing that. They're making code which can crash at any moment, basically. Because floating point numbers do not work the same way as integers. Integers even also can flip, you know, back from, if I reach the top, I can start getting from 0 if it's unsigned, right? But the floating point, it's even easier to break. Floating point numbers can be broken by, let's say, giving large number on integer part plus or multiplied by a small number on decimal part, and you can break the number basically. So and this is like for any programmer 101 very important information basically. So that's that. So torch, oh sorry, so I have torch logarithm here. Logarithm, yeah. So this is that part, and this is now done. So loss function is done, and now we need to just make the training part. So 17 slide. So and here here we also will calculate accuracy, right? The model, not only the loss, because loss gives me the value, right? And I don't know how accurate is my model. I just say like, okay, loss is like, let's say 0.003, what it means actually. So so accuracy is a great way to measure your precision, right? So how we do this? Y prim equals, whoa, so let's see. So y prim equals the model forward, I believe, yes. So model forward x classes. And now loss function. Actually, these parts we could just copy from the previous template, but let's practice y prim y and losses append loss item. And now I just maybe, okay, not copy because you need to write as well. Data, you need to train it. This is exactly the same way. Nothing changes here. Only there will be the accuracy calculation. So loss backward. This part calculates the grad values backward. Oh, is it correct? Yeah. Grad values for the weights. Then optimizer step. optimizer step. By the way, I can give you one small hack here. So 0 grad. I think in this template I did not change radam. So sorry if I scroll up here. See there is SGD. Please change to radam. This will be better results for you. So if you optimize a radam, not SGD. So that's that. So if you scroll down here, now there will be this thing which I told you before, that we need to move from Torch to NumPy to calculate the accuracy. We can actually calculate accuracy in Torch as well, but this will not be convenient. So how to calculate it? Y index. This will be the real index values. What I mean by indexes, again, it's something like this. So if I have these the petrol, diesel, LPG, CNG, the index value here will be 1, right? If I have this will be LPG, then index value will be 2. And how to get from that to that is in this way. So Y data. So remember, we always have data on grad. Data. Then I call NumPy. So this means please change tensor to NumPy format. And in NumPy we have argmax. On argmax we will tell axis -1, the last axis. So it will, the y axis -1, because right now we have situation like this literally. I have this guy here who is like the first sample of the car, second sample of the car, and so on. And I want them to be changed in the minus axis, the deepest axis there is, to 1, 2, like this, okay? So by the way, yeah, so this is the thread of that. So what I'm now doing, I will just show in 2 lines how to calculate accuracy without many for loops and so on, right? So we'll just make it like this. So then y prime index. So this will be now the predicted values, not the real values. This is exactly the same stuff, just copied here with y prime. And here, this is a beautiful thing about this is that what actually this will happen is that it will not be as on top there, but there will be like this. There will be 0.99901, like, and here will be, let's say, 0.80, 0.2, and it will still produce as the integer numbers, okay? See, like, the first line is the real data, right? Real car values. The second line is the predicted car values, which have these nice distributions with 80%, 20%, and so on. But to compare them together, it's quite difficult, right? You could have the for loop with confidence threshold or something like that. But what we can just do is do the argmax and produce what are the numbers of the maximal columns, right? So, and if I have these 2 lists, it's very easy to compare them now. So just for the sake of example, let's say that for the second car, model was not right. So the model accidentally predicted that this should be a petrol car. So 622, like this, and then this would give us the value of 0 here, because this is the first column, right? So that's that. Then what we do is we calculate accuracy, and how we calculate accuracy is really cool. So we can do exactly like this. So we will just take first list, compare to the other list, then we will convert it to the float by multiplying by this, and it will produce as the average accuracy. So how it actually works. So it will do this. So if I have these 2 lists, 1, 2, compared with 0, 1, 0, like this, 1, 0. It will give us true, false, equal. So this will be the output. And then after I multiply by 1, it will give us 1, 1, 0, because false is always 0. And then after that, I will just calculate average, and this will be 50% accurate. Okay? Cool. So this is, I literally gave you a small formula how to avoid huge loops and so on, and just to calculate accuracy. So if you write these 3 lines of code, you're able to calculate accuracy for your classification models. So I will drop this to the whiteboard, and then we will start to run it. We'll see if our model is able to classify these cars. And by the way, well, if we have a little bit of time, few minutes, maybe we will be able to also add those coefficients, because it will not work great right now. So if I run it, let's see, run it, because I have very little cars of LPG and CNG. So if I run it, let's see. Okay, now I have training. Oh no, that was dataset. Okay, so now I have training running. Training accuracy is already 85% accurate. So let's see after 10 epochs. Oh, okay, this failed because of confusion matrix. Okay, let's add confusion matrix as well now. Otherwise, for the home task, it will be difficult to understand. But confusion matrix is something very, very simple. So confusion matrix is just statistics. It is just please count samples which falls into a specific category. So however we could do this. So let me show you. So here, under the accuracy. So under the accuracy for, let's go through each car in my dataset. So each car index in range of, we could call batch size, but but remember sometimes batches might not be the same size. So that's why let's use y indexes, whatever. It doesn't matter which variable you use. This is basically batch size. So 0 till batch size. So that's that. Then I'm going to confusion matrix, and when we will run this, you will immediately understand what it does. So confusion matrix, and in confusion matrix we will select two different row and column. So the rows is the first. Rows will be the predicted values in this case. Predicted indexes, prim indexes by index. And columns will be the real. And what we will actually do, we'll just add one value here, +1. So this is statistics. We register how often we get things right. So if both of them are the same, the y prim and y index, we will put this value in a cell which is diagonal of the confusion matrix. If they are not same, it will be somewhere on the sides. So basically, literally these two lines of piece of code, and then I can run the code and see nice results, hopefully. So I'm putting this here. Now let's run this code. So last time I got 85% accuracy after the 10 epochs. So 84, 80, oh, okay, on the test, yeah, 85, 85. Okay, so yeah, we'll see this very nice picture already. So basically, I put this also on the Jamboard, this piece of code on the whiteboard, I want to say. Right, so this, yeah. So see, what's happening here? So we have a training loss and test loss, and we have accuracy there. So the blue is the test accuracy, which is lower than the train accuracy, and this is the confusion matrix, and it just registers how many oftentimes when the real value was diesel, the predicted value also was diesel. When the real value was petrol, predicted petrol. What we can already see why we are stuck at 85%, because the model is completely ignoring LPG and CNG, because they are very little samples of them. So what we could do is we could add weight to every time when we'll see CNG and LPG, so that loss function goes larger steps in those cases. So like a higher, by the way, we also see overfitting now. So we need to save model at 10 epochs basically. So let me see, while you're trying to get this run, if you have some bug, is it error somewhere, somebody? Okay, cool. Then I just let me quickly see if I can help you with that weighting stuff. So let's see if I have some example about weights. There are many ways how to calculate weights, by the way. There's not just one way how to calculate weights. We'll just look which formula I would like to use. Weights. weights. Okay, let's use some simple one. Okay, so let's like 5 minutes. Let's make some small weight stuff here. So here on the 45th line for the weights. So what we could do, there is a really nice Python function called counter. So y counter, and what counter does, it just counts occurrences of the same class in the list, Python list counter. So this will just give us that the LPG cars are so many, other cars are so many, and so on. Counter, yeah, cool. So and then counter, we want this to be. We don't need the index values. We just need the count values. So array list of y counter values. And then one formula that I can give you, but there are many formulas which you can use, is 1 divided by this. 1 actually is just a scalar. It can be also 10 divided by something. 1 divided by y counter value multiplied by np sum of all values. So by the way, it's from this part of it's very difficult to understand what is the output, but basically, so here, let me show you. So here it actually would give us the how many cars we have, petrol cars. So like let's say 3,000 petrol, 3,000 diesel, and then let's say 200 those and 200 and let's say 150 those. And then afterwards, after we apply this formula, we would get that let's say, so this will be some kind of 0, 0 something, 0, 0 something, and this will be, let's say, 3, 4, something like that, so that there will be attention to these rarer classes. And again, I'm saying that this is not the only formula how to calculate weights. You can have the 10 divided by something. You can have completely different formula. It's just the idea that we need to somehow change the distribution. So that's that. So the weights, and then to implement weights, it's really simple. So let's see, where do I? So this should be go in the loss function. Loss function. So yep. So loss function here we'll have weights calculated. Weight equals torch flow tensor. Dataset full. Oh, there should be y weights somewhere. Y weights, yes. Y index. Where's the y index? Right, I don't have y index. I need to calculate, unfortunately. So y index is the same code as I had before. Y data numpy arg max axis -1. So this will be the y index. So these will be the real classes that I have. And then I need to add an additional dimension. So unsqueeze. So if you debug code, you would see that this actually adds another bracket, just another bracket. So, and then I can multiply it in here. And now, after I run this piece of code, it should be now focusing much more on rare classes. So basically, this is already one loss function engineering that I showed you. So if I run it, and for the home tasks and for some of the tasks, we'll look. By the way, the loss is now, the accuracy is now much lower because now it's starting to focus on the rare classes, and it is more difficult for the model to learn all of this stuff. I put this on the whiteboard as well. but there is also a missing F1 score. So somewhere here is the F1 score. F1 score is just a calculation of how this matrix is good. So if every value is on the diagonal, then we have F1 100%. But if I'm just looking at accuracy, it could mislead me, because maybe some values are 90% and one is totally wrong. So that's why F1 score is also really great, and you should look at that as well. Now it's trying to predict LPG and CNG, but it's mixing them both up. But basically, we need to work on that. So yeah, so I think this is about it for today. The next week I will update you where we will have the lecture, because I'm also holding in Riga as well the lectures. So if you by any chance in Riga, you can go to Riga as well. Also a cool campus, really large, right? So also either online or so. But we will look at image classification on so it's already starting to get interesting. Okay, so yeah, please then, if you could look at these small subtasks which you did not look at together, and you can also do these homeworks. And specifically, if you want to do your bachelor master thesis with these things, and I could be also your like supervisor and so on, you need to work a little bit on this. So because I assume when I work with some students that they know all of this already. So okay, so that's it for the